atom. This was around the time Michel then moved to Yale since around 2002. After he also became the director of research at CEA Saclay, and since 2002 he is the F.W. Beinecke Professor of Applied Physics at Yale University, where he focuses his research on experimental solid-state physics with an emphasis on quantum mechanical electronics or contronics. He's currently focused on looking at new phenomena of fault-tolerant quantum memory and remote entanglement. He's also working part-time in Google for the past 1 year or so. His other accomplishments are that he's a member of the American Academy of Arts and Sciences and a member of French Academy of Sciences. Michel has received the Ampere Prize of the French Academy of Science together with Daniel Estève and the Descartes-Huygens Prize of the Royal Academy of Science of the Netherlands and the Europhysics Agilent Prize of the European Physical Society together with Daniel Estève, Hans Mui, and Yasunobu Nakamura in 2004. He's also a recipient of the John Stuart Bell Prize, which he received jointly with Rob Shulkoff in 2013. And in 2014, he was awarded together with John Martinez and Rob Shulkoff the Fritz London Memorial Prize. There are many other accomplishments, but I think to keep it brief, I will stop here. I'll just say something about the topic of his talk today, which is related to quantum error correction, which is probably one of the most important goals in the field of quantum computing in the near future. And it is really an amazing piece of physics and technology, which is probably the main reason why people hope that quantum computing will be a practical technology someday. And it sounds very strange and fascinating because you're trying to take a lot of bad components and make a good component out of that. And Michel's group has recently made some important contributions to this and achieved an important milestone of actually demonstrating that error correction truly works in the sense that the combination of these elements, which by themselves are not very good, but when you put them together, they actually demonstrate a better performance. So welcome again, Michel, and over to you.
Okay, thank you very much, Vijay. For this kind introduction. I regret not to be in India to give this talk, but thanks to this video technology, I can present it from the pretty much another completely opposite time zone. As Vijay just mentioned, I'm going to present to you the results of a recent experiment we did at Yale University. And indeed, this experiment answers the question whether we can assemble faulty parts and make a qubit out of these faulty parts, which will be better than the best of these parts. And so I have, you are seeing the list of authors on our recent work, which has been published in Nature. But I have written here also previous papers that paved the way towards this recent experiment. I would like also to present the picture of the people whose data I will show, and in particular here you see Alec Eichbusch and Vlad Sivak, who took many of the data that I'm going to present. Vijay, I heard the message saying that the recording has stopped. So is this a technical problem we should address, or should I continue?
Maybe let's just pause for 1 second. Professor Deshmukh, any idea what happened?
Yeah, I think we can continue. It will be taken care of.
I think it's anything, so it should be okay. Please go ahead.
Okay.
Yeah.
I would like also to mention my various colleagues at Yale, with whom I have this long-time collaboration, in particular Rob Shulkoff, Stephen Gervin, Leonid Glassman, and more recently, Shruti Puri. Okay, so this is the outline of my talk. There's 3 parts. In the first part, I'm going to review for those of you who, for whom superconducting quantum circuits is not a specialty. I will give an overview of also the principle of error correction. Then I will dive in the code that we have been using, which is this Gottesman-Kitaev-Preskill code, which is abbreviated by the letters GKP. It's as you're going to see, it's a very effective code, even though it was discovered more than 20 years ago theoretically. It's just it has just been implemented in practice very recently, but it's a very efficient code. And then in this last part, I will give you more details about our experimental setup, and I will present the recent results we obtained this year. So on to superconducting quantum circuit. The best way, I think, to introduce them is to consider an LC oscillator that every student really sees in some introductory electrical engineering course or electromagnetism. There's an inductance, there's a capacitance, but here we're going to suppose that these elements are made of a superconducting metals, and this circuit is cooled at very low temperatures. Under these conditions, there's essentially only 1 degree of freedom in the circuit, which is the circulating current. But you can also think about the flux through the inductance, and the conjugate variable of the flux is the charge on the capacitance here. Quantum mechanically, those variables, which are collective and macroscopic, if you take quantum mechanics seriously, you will see that the flux variable and the charge variable are actually conjugate variable, and their commutator is exactly the same as for position and momentum. This circuit is linear. It has the same Hamiltonian as an harmonic oscillator, and the energy will be quantized in units of h bar omega at resonance, and which is 1 over square root of LC. The problem with this circuit is that it cannot be fully controlled. It is too linear. If you shine a microwave, RF excitation on this circuit, you will simultaneously excite all these transitions, which are degenerate in frequency. And actually, you cannot this is some general law of physics. If a system is fully linear, is perfectly linear, you cannot actually drive the system to an arbitrary state. To prove this point, let's suppose you had actually put the system in the ground state. Well, when you shine a microwave, you will actually create superposition of all the excited state, because all these transitions are degenerate, and then you cannot, for instance, go to the first excited state only, and only that state. In order to fully control the system, you have to have some nonlinearity, which means that the potential energy has to deviate from a perfect parabola. A simple flaring up of the potential will be sufficient. Then all these transitions here between neighboring levels will be non-degenerate, as shown in the spectrum here at the bottom. And we can define the nonlinearity ratio as the difference between transition frequencies divided by the sum here, or the one of the frequencies. What is really important if you want to realize a quantum computer is not simply this nonlinear ratio. You want the nonlinearity to be bigger relative to the line width in general, because there will be always some remaining dissipation, this spectrum is not composed of infinitely sharp lines. There will be some broadening due to the dissipation. So what you're interested is in maximizing this product. The Q factor, which is the ratio of the frequency to the width here, times this nonlinearity. And if you analyze the progress in quantum computing with solid-state physics system, there's been a big focus on maximizing this quantity here. The better it is, the more powerful these quantum computing experiments. In our own field of superconducting quantum circuit, we rely on one component, the Josephson tunnel element, which is represented here. It's a sandwich of two superconductors separated by a thin insulating barrier. And this component is indeed a nonlinear inductance. I have represented the potential here. It is actually a sinusoidal potential, but we use in general one arch of this potential in our experiment. And you can view this Josephson element represented as a cross here as a sort of nonlinear inductance. It is it has the virtue of being an inductance with no fundamental dissipation. It just like the capacitance here, if you make it sufficiently cleanly, can be a capacitance without you can actually remove most of the dissipation in the capacitance. The Josephson junction has no fundamental limit in terms of dissipation. In principle, we can make this element essentially perfect. So with these systems, because it has quantized energy level, what we do is that we single out the first two levels and declare this manifold here as a qubit, a two-level system. This, more generally, what we call a physical qubit is usually the manifold comprised of the ground state and the first excited state. So basically two energy levels separated by one excitation. And as you know, this two-level system can be represented by a Bloch sphere with a vector, unit vector, represented a pure state in this manifold. The aim of quantum error correction is the following. In reality, because of noise and residual dissipation, you can view this physical qubit as being submitted to random fields along x, y, and z. And this will shake this Bloch vector and introduce decoherence. The phenomenon, the basic phenomenon behind quantum error correction, which was recalled by Vijay, is that if we take several of these qubits, we should it should be possible by a cooperative effect to actually create a better qubit out of these faulty parts. By the way, I would like to mention that the discovery that this is theoretically possible was made also by Peter Shor, and I consider this an even greater discovery than the discovery of the factorization algorithm. At first, people could not believe that this was possible. Classical error correction exists, of course. By taking several classical bits, you can make a better better bit by some techniques such as majority voting, but these techniques rely always on the measurement of the bits. And in quantum mechanics, measurement is invasive. So it was thought that at the beginning that quantum error correction could not exist because detecting and correcting errors mean you have to measure, and measurement can be destructive. Actually, it is now known that it is theoretically possible to make a perfect system out of imperfect part, and there are actually two great families of encoding. So in the first family on the left, you encode the information in a register of little n physical qubits, like shown here. And you get a redundant Hilbert space, a bigger Hilbert space you started from, with a big n equals 2 to the n dimension. And this is the method that is used in the STIN code, the surface code, color code, and so on. And this has been demonstrated recently at Google, for instance. There's another type of approach, which is nicknamed continuous variable approach, in which you use as a redundant Hilbert space, the space of an harmonic oscillator. So if you have, let's say, big n levels that you use here, that will be equivalent to a log in base 2 n of qubits. And the first code of this kind which was invented is precisely the GKP code, but more recently CAD codes, binomial codes, Keaton codes, and so on. All these bosonic codes have been using this type of ideas. There are these two strategies have both their advantages and disadvantages. The problem of discrete variable encoding is that you need one Josephson circuit per physical qubit. On the other hand, the continuous variable encoding needs only one Josephson circuit that actually provides the nonlinearity for operations. Because if you just have an harmonic oscillator, you have this interesting encoding, but you cannot act on it, and you need some auxiliary nonlinearity. Because this has a minimal overhead, this was the strategy that we have pursued in our recent experiments on quantum error correction. Now, when we say that out of these faulty parts we're going to get a better logical qubit, what do we mean, basically? Well, we mean that the logical qubit are encoding information in that larger Hilbert space lives longer than the best of the constituent physical qubit. This is what we mean in saying that we are doing error correction, and in particular that we are going over break-even. So if you have a logical encoding, you can actually define this average fidelity here by this formula. And what we call the quantum error correction gain is the ratio of the minimum error rate here at the numerator, the error rate of the best qubit, the best constituent in the system, divided by the error rate of this logical qubit. And we call break-even the situation where this gain is exactly 1. And as I'm going to show, in our recent experiment, we have doubled this error correction gain, making a logical qubit that lives twice longer than any constituent qubit. What we've used is this GKP code, as I mentioned, and I'm going to spend some time explaining this code. how it works. First of all, I would like to introduce the notion of the representation of quantum states of an oscillator by their Wigner distribution, which is a quasi-probability distribution in phase space. So Q and P are the two variables, conjugate variables of the oscillator. And the vacuum state, which classically would be a point here centered at 0, 0, is now some kind of fuzz disk because of 0-point fluctuation. When you add one photon in the oscillator, you modify this quasi-probability distribution, and it has now a node here. So this is the n equal 1 Fock state. The n equal 2 Fock state, 2 photons as 2 rings, and so on. If we, but we can represent other interesting states in this manner. For instance, the coherent state or Glauber state is just a displacement of the ground state. You just here move, the ground state by 2 units in this frame. You can do other transformation. You can squeeze this vacuum state, so you can reduce one width at the expense of the other, like in this picture. Or you can also superpose coherent states, and that creates what is known as a cat state, where you recognize the 2 blobs here, the plus alpha and the minus alpha, and then you have these beautiful fringes in the middle. The fringes that exist in two versions, depending on whether you have a plus or minus sign here, and this is what is called the cat state encoding, and I'll come back to this at the end if there is time. For the moment, I'm going to concentrate on the squeezing vacuum. And just like the cat state is the superposition of 2 coherent states, here we're going to consider superpositions of the squeezed vacuum. At this point, it's easier to talk about wave function. So I have this Q coordinate here for the oscillator, and I represent the wave function of the state here. And it's going to be a superposition of squeezed peaks here. And this will define what I call the zero logical. Now, the one logical is very easy. It's the same state, but displaced by half a period. And then I think you may be seeing the advantage of this code. As long as the noise here, the noise in Q, has not shifted the state by more than half the separation between the green and purple peaks here, you're fine. You can still say that an error has not, you can detect this shift without actually looking at the state and then correct. This looks like a very convoluted, very complicated way of encoding information, but it has been actually shown by the group of Steve Gervin and Liang Zhang that actually this code is the most efficient if the errors that you have to face are the photon loss in your oscillator. So when we learned about this, we understood that actually this code, even though it looks exotic, is actually something very interesting to implement. This is now back to phase space. This is the theoretical Wigner function of the GKP encoding. You see it consists of a series of blue and red dots. And I could say that to caricature the idea here, this GKP encoding is efficient because it is a pure interference pattern. There's no blobs. that are somehow classical. In phase space, you see we've constructed a pure interference pattern, and this is one of the reasons which give its code its power. I have represented here the unit cell in this interference pattern, and you can better see here why the 0 and the 1 are different. The 1 and 0 are two shifted versions of the same pattern. And I cannot resist really telling you why this code implements a qubit. How can you, it's not so easy in this kind of wallpaper to see why we have a qubit at all and what are the operations, how can we act on this qubit so that we move around the Bloch sphere. So now I'm going to use a very, very important concept, which is the geometry of translations in phase space. Classically, if you compose two translations in phase space, like a translation by U and a translation by V, you can return to the origin and nothing changes. But quantum mechanically, there is a phase factor. And the beautiful thing is that this phase factor is given by the area in phase space divided by the Planck constant. And what is amazing is that this is all you need to know. Quantum mechanics is this, the apparition of a phase factor in the composition of translation in phase space. If you're interested in this idea, this is a little book that explains this, what the authors called a third formulation of quantum mechanics, which was actually found essentially at the time of World War II and was never publicized very much. I'm writing exactly.
Hi.
Yes.
Hi, can I interrupt? So in the previous slide, I do not really understand how are the zeros and one distributed. Like, how do you make sense of that diagram in the last slide?
Yes.
With the red and blue dots.
Yes. So what I am saying is, is the message that the inventors of this formulation of quantum mechanics took pain to explore, and is that classically, when you translate, you do some closed circuit in phase space. When you come back to the origin, you are in exactly the same state. There's no difference.
Yeah, sorry. Actually, my doubt is more fundamental. It's from the previous slide. So where you have those blue and yellow circles representing in the phase space, you say that one of them represents a 0 and another configuration represents a 1. So how do you make sense of the diagram on the previous slide? Can you move back to the previous slide, please?
You mean the previous slide like this?
Yes,
Oh.
yes, this one. Yes. So I see a partition in between saying that this configuration represents a 0 and the right configuration represents a 1. So is there anything particular?
But what I'm representing here is the Wigner function. And now I'm going back a little bit, I'm backtracking the argument, because if you want this showing you the Wigner function doesn't explain at all why the states spanned by 0 and 1 have anything to do by a qubit with the qubit. This is actually two states of an oscillator. They are different, but we don't even understand why they are orthogonal or why would they actually span a qubit, you see, and how we would act on them. So the purpose of this new slide here is to give you a hint of how this works. And in order to explain how this works, I have to point out the fundamental difference that there is in the geometry of phase space classically and quantum mechanically. If you the problem is that you can use some of your classical intuition, but you have to introduce a huge modification, which is that closed circuits in phase space quantum mechanically will create a phase. So when you return to the origin, you are not necessarily in the same state. You have actually
okay, you might have gotten a certain phase when you come back to the same position.
Yes,
right.
And this statement is that curiously, and that's not very well appreciated, the introduction of this axiom is all you need actually to go from classical physics to quantum physics. And and I'm going to use this property to explain this GKP encoding, because it is based on this important remark. Okay, so if we translate this law of the product of translations into complex numbers, which are usually the way in quantum mechanics we parameterize displacement in phase space. So we have these displacement operators here, and basically when you compose two displacement, you use this complex number alpha and beta to parameterize these two translations, and this is the phase factor written in the usual way of quantum mechanics textbooks. Okay, now comes a very important remark. So if you make two orthogonal translations and you choose their argument correctly, such that the area enclosed by these two translations is exactly a two-action quantum, then not only these two translations commute, in general they would not commute, but for these particular values they do. But these translations will be called, will actually serve as what is called the stabilizer of the code. So you can measure these two translations independently. They do not interfere with each other. And what they do, if you declare that these translations are actually identical to the identity, it means that you have actually made the phase space into a topology of a torus. So this diagram here is a bit probably a bit more explicit. So we've declared this translation to essentially be the identity in our code, this translation 2. Now, you see, if we take half of this translation, we can call it x in the sense that x squared is equal to I. So doing this x 2 times is the identity. Same thing with I here, on the vertical, half of it will be our z operator. And our y operator will be a translation in the diagonal direction. Now, why is this implementing the polyalgebra? Well, you see, this whole area here is two-action quantum 4 pi h bar. But this triangle here, so this is elementary Euclidean geometry, x, z, y. This triangle has exactly 1/8 of the total area here. So the phase factor is pi over 2 here, and which means that you have implemented a system in which the product of these three translations is equal to I. And that's exactly the polyalgebra. So this gives you a better sense, I think, of why using states in phase space and using translations as poly operators can actually implement qubit. So in practice, you cannot have this infinite set of squeeze states or infinite set of points in phase space. Your code will be consist of points, but these points have a sort of 0-point spread. And the Heisenberg-Uncertainty relation is involved here. If you want the code to have finite energy, which means that the envelope here has to be finite, it cannot extend to infinity, then by reciprocity, quantum reciprocity, the points have to have a sort of spread here, which is represented in this figure. I have represented some marginal distributions here. And so instead of having infinitely squeezed states, a picket fence wave function here, I have a few peaks. And this is pretty much a representation of what we achieve experimentally. We have to be careful. So I should describe now the arrows here in this diagram. So you have two types of arrows. You have these little blue arrows, and the error correction code will make these arrows, will implement these arrows, which are effective forces that sharpen the peak. On the other hand, we should balance this sharpening of the peaks by the trim of the envelope. So on the outside here, you see these purple arrows, which also constrain the envelope. So we have to strike a balance. We need to sharpen the peak, but we need also to trim the envelopes because of this reciprocity. So for instance, if we sharpen the peaks if we trim the envelope in the p direction, then we will enlarge the fuzz in the q direction. Okay, so this was in a nutshell the principle of this GKP encoding. Let me show you how we in practice implement this code. So yes.
Just here, just a quick clarification. So in the picture you just showed us in the slide before, again, the 0 and 1 logical would just be like shifted patterns of this restricted phase space.
Yes. So yes, so let's go back. So this picture is showing a random superposition of 0 and 1 logical. So what is represented here is the code space. So it doesn't in the center of the picture you don't have one state in particular. What I have represented is the sort of impure state composing of a random superposition of 0 and 1. It's this is called a representation of the manifold. But if you're interested in one particular state, then I have represented on the side here what would be the marginal distributions of pure states in two cases. For instance, here on the top, you have plus z and minus z, which are the 0 and 1 logical. But on the side here, these are the eigenstate of plus x and minus x. So these are the even and odd superposition of the two logical states. And you can see that if you have a random superposition of these states, then instead of having peaks on certain lines here, you will have actually peaks everywhere.
Yeah, got it. Thanks.
Yeah, so you can see why actually this picture in the center represents the manifold. So when you represent the manifold in this way, there's not going to be any blue blue part in general for this code. For other codes, even the manifold can show negative negative Wigner function. But for GKP, when you represent the manifold, you lose the blue parts. Okay. So how do we do these experiments? Well, we need a cavity, so an harmonic oscillator. In this case, we choose a 3D superconducting cavity made of aluminum, and the code words are going to reside in this cavity as combinations of various states. But we need to act on these states, and we do this by using what is called a transmon qubit. Here it's an auxiliary transmon qubit. It will serve as a manipulation for the manipulation of this state. And because we're doing a quantum error correction, we have to remove entropy in the system. So periodically we are going to read and reset this auxiliary transmon qubit, and this is done by a combination of this readout resonator here and this readout port here. So you can view this part here as the way entropy is removed from the system. At the same time, we need also to manipulate this cavity state, so we have another control port here. But this port doesn't evacuate the entropy. The part taken by the entropy is this part. And here on the right, I am giving you a few numbers. Actually, these are the specialists of superconducting circuit. We recognize a few characteristics here. One important aspect of this experiment is this rather favorable lifetime of the auxiliary qubit. You don't want to degrade the experiment too much by having a transmon qubit here, which is too bad. So this is a sort of state-of-the-art transmon, which was made with tantalum, the tantalum technology that was recently developed at Princeton. Okay, so how do we manipulate the state of the harmonic oscillator, and in our case, this superconducting cavity? Well, there's a powerful operation which essentially does absolutely all that is needed to do a quantum error correction and manipulate the state. And I've called it the Swiss Army knife of this GKP encoding. And this is a gate which we have called conditional displacement gate. And what does it do? Well, it let me first explain how it is done in practice. So we have this cavity here, superconducting cavity on the left, represented by this red rectangle. We have this readout resonator here. But between the two, we have this ancillar qubit, and we can shine microwave both on this ancillar qubit as well as on this superconducting cavity. And with the combination of these two signals, and which are represented here, when I work out the Hamiltonian and see the various cancelling of terms, so it's a sort of double echo protocol. When I arrive at the end of this gate, which lasts about 1.5 microseconds, I will have displaced the initial state here, which I have taken here squeeze state, but it could be any state in the phase space of the oscillator. I will have displaced it by two opposite displacement, depending on whether the qubit was in the G or E state, this ancilla here. And astonishingly, this gate can do essentially all the functions that we need for quantum error correction. This gate can be done over and over with different parameters. There's this parameter alpha here, which says in which direction and by what modulus you have displaced your state in phase space. So you can vary this parameter here. And what you can do also is rotate this auxiliary qubit. And by a combination of these two actions, you can create a sequence here which is able to do what you want. In particular, you can prepare a GKP state. So this is, for instance, shown here. We can, these are the Wigner functions of various states that we can prepare in this way, that we can prepare the plus z eigenstate, plus y minus x, and so on. Now, what is great is that you can use this gate also to do a measurement of the errors. You can use the sort of reciprocity principle. You know that when you act on a state, you can actually, when you control, let's say, the state of a quantum system from another quantum system, there's a back action on the controller system, and this is what we use here. So suppose that our cavity has been, the state in the cavity has been shifted by a small amount epsilon here in the q coordinate. Well, using this algorithm here, we can transfer this displacement, we can transform this displacement by a rotation into a rotation of the ancillary qubit. We have prepared the ancillary qubit in the equator. Here we've taken the block vector in the equator, and we can essentially transform this displacement into a small angle. Now, if we measure the qubit, we are going to get 1 bit of information on this displacement. And by repeating this measurement over and over again, we are going to learn the errors. Of course, you understand that one crucial point is that this conditional displacement gate has to be very carefully calibrated. We have to know exactly which alpha we implement. So we can do this kind of Berry-phase oscillation experiment by preparing a qubit in a superposition of E and G, and doing control, this sequence of control displacement. We will turn in, let's say, counterclockwise in phase space if the qubit is in E, and turn clockwise if the qubit is in G, and that creates an interference pattern that allows us to calibrate this parameter alpha. And you see these experimental oscillations which we have used to calibrate our experiment here. One recent novelty in this GKP encoding was the discovery by Baptiste Royer, Shadra Singh, and Steve Gervin that there was a possibility of autonomous error correction. This is very important. So when you want to correct an error, you don't want necessarily to record a measurement and do measurement feedback, which in superconducting circuit was realized the first time at Berkeley, and the Vijay was actually the lead experimentalist in this experiment. So the problem with measurement feedback is that it takes a certain amount of time to react. There's this latency, and having a code that is corrected in a sort of autonomous manner without any signal needed to go back to your experiment is interesting. And this protocol here, which I am showing in the bottom part of the slide, does exactly that. It without any measurement, you can evacuate the entropy in the auxiliary qubit, the entropy caused in your system by the noise. You can evacuate it in this autonomous way. And all you need is to reset actually the auxiliary qubit. You don't need, strictly speaking, to measure it and react on the system by some kind of outside electronic. Simply resetting the qubit evacuates the entropy. So how does error correction work exactly in the system? Well, these block spheres here represent the sort of principle of the error correction. So our cavity, because it has a redundant number of levels, in fact, it has an infinite number of levels, maps the information in this way. You have a ground state manifold, what I call ground, the GKP encoding. So this is in black. But if an error occurs in the cavity, you are transforming your ground state manifold into an error manifold. The virtue of this code is that the basic errors simply move the manifold without scrambling it. So when an error occurs, actually you can have two transformations. A photon loss A will go to this manifold, and an excitation, if there's a spurious photon added in the cavity, you go to this manifold, and so on and so on. Of course, depending on the size of the code, there will be an horizon here at which this nice process will stop. Instead of just moving your information from one manifold to the other without scrambling it, you will actually start scrambling it. So up here in this slide, you begin to scramble the information inside. But what is important is that, if you have only infrequent errors of one photon excitation and of the photon excitation, your information is not corrupted. The aim of the error correction is to make sure you don't go too far in this ladder up. So if you have installed some kind of dissipation, which is represented by these green arrows here, you will stabilize your information in the ground manifold, and only very rarely will you, by a sort of Brownian motion, climb up here in this ladder and make an uncorrectable error. So I think this picture tells you why you are likely to make less logical errors than the rate of basic errors. The basic errors move you up, but as long as you have these green arrows be sufficiently effective on the scale, on the time scale of your basic errors, and if this horizon here is sufficiently far above, you will be fine. You will be making an exponentially small number of logical errors. It's basically you will have a sort of Arrhenius law work for you. I would like to describe another aspect of the experiment, which in practice was crucial, which was the use of reinforcement learning for calibrating the gates that we are doing. I'm not going to go too much in this topic here. I have some references at the bottom of the slide if you're interested. Okay, so does this error correction really work? Well, here it is shown in action. So we have prepared here two states, the plus z and the minus z. And these states are attacked by errors, but we actually correct the errors, and it's only after about two about two milliseconds. This is the sort of average lifetime that essentially we completely destroy the information. Actually, we can reproduce this experiment by starting from different states, and these are the consolidated results. So in this experiment, we first measure the quality of the constituents. So for instance, we measure the quality of encoding the information in the ancilla, and we see that here the lifetime is 250 microsecond, more or less, if you average over all states. If you encode information in the cavity itself as a superposition of 0 and 1 state, which 0 and 1 photon, this is not correctable, of course. You get a better lifetime, about 800 microsecond. But if you combine both these constituents, both the cavity and the qubit, with this GKP encoding, you see you can get a much longer lifetime. What I'm representing here is the open dots are the lifetime of the GKP encoding if you do not do any error correction. And you see the information dies rather quickly because you are using more than 1 photon here, so it decays faster. But when you apply the protocol, you get actually a much longer lifetime. Not only you beat the native encoding, but also you beat the constituent qubits. And here you have an average of about almost 2 milliseconds, which represent a factor of 2.3 better than the best constituent encoding in the system. So this is why we say we are breaking, we are going above break-even by a factor of actually more than 2. How does this result compare with what is done in other platforms or with other codes? So this is our result. This is the improvement of the coherence. It's represented by this green arrow up, and this is done in about 350 cycles of error correction. And this is interesting because of this number of cycles, we can analyze exactly what is going wrong in our error correction, why it's only a factor of 2 above break-even and not better. But you see that if we compare with the other encoding, and in particular with the present stage of the surface code, we do get really a sizable improvement. In all the surface code experiments at the moment, in terms of absolute lifetime, you take a loss. When you apply error correction, you get a lifetime for the encoding information that is less than what you had started from in your constituent qubit. Okay, I think I have probably exceeded my allotted time here, so I will just conclude this talk. Our result is that we've achieved this lengthening of coherence. So we've made a qubit that was more coherent than its constituent parts by a factor of 2. And I would like to point out that there was a great contribution here to a better ancilla transmon qubit, which in our case was produced by Ganjam Suhas. And there's also this modern neural network techniques of reinforcement learning was definitely an advantage in calibration of the experiment. So this is also an interesting new aspect of quantum circuits. Where are we going? Well, obviously, we need now to show that we can improve gates, and in particular, CNOT gates. And this is an experiment which is in progress. The nice thing about this encoding is that the CNOT is a particularly simple operation when you view it in phase space. This kind of operation has actually been done with quantum limited amplifiers, for instance, in Michael Hatridge's lab here. You have to do this while error correcting, of course. And I will not say that the bosonic codes are the end to quantum error correction. They are a very useful intermediary stages. In particular, they can be very hardware efficient first layer of encoding of logical qubits with, of course, the layers above realize more in the spirit of the surface code. And on this note, I would like to thank you for your attention. And I am now ready to take questions.
For that excellent talk and really fantastic results. We can now take some questions from the audience. So those on the Zoom can just raise your hand, and then I will go through the list. And I guess one of you is managing the YouTube questions, if there are any from there.
No, I don't see any questions on YouTube. There are no questions as of yet.
Okay, Anish, please go ahead.
Hi, sir. Am I audible?
Yes.
Am I audible? Yeah.
Yes, yes.
Thank you so much for that talk, sir. You mentioned using reinforcement learning to calibrate the pulse gates, but can you elaborate a little bit on the parameters that you were using, or what parameters was the RL agent trying to update or improve? Was there some sort of a drag parameter or other degrees of freedom that were being optimized?
Yes, so maybe one one important parameter that I should mention here. So first, I have to clarify what we call a QEC cycle, with quantum error correction cycle. This is about 5 microseconds. The gate itself is 1.5 microsecond. So you see, but the kind of error correction we apply is this combination of qubit rotation and conditional displacement. We have I have knee in front of because we also call this conditional displacement echoed conditional displacement because of the echo nature of the gate here. It is robust to various kind of errors because of this echo. If you zoom in a little bit on the pulse shape here, which where you see so each part here is an echoed conditional displacement. You see that it is based on essentially Gaussian pulses that are sent to the qubit. We don't need to apply drag. So, by the way, in this echo, in this sequence, you see both the imaginary and the real part. The imaginary part is in dashed line, so you have both I and Q channels represented here. We use Gaussian pulses, and we don't need to use things like drag because the time scale here, the transmon is way sufficiently anharmonic, so that we don't have to worry about these details. But what I want to say is that the reinforcement learning will adjust the amplitude, phase, and all the timing of these pulses. So maybe I should, I can give you an example of why reinforcement learning is very necessary in this experiment. So when you look at this protocol, this is the theoretical protocol. You see that these two gates on the side of the middle gate have the same parameter epsilon here. Now, the reinforcement learning was allowed to modify these parameters here and to make them different. And it found actually that the optimum was when these two parameters were had pretty much a factor of 2 difference. And this was to compensate some skewness. You see, there's a lot of things you don't know when you start the experiment. So you have an idea of the Hamiltonian, but there's certain skewness in your Hamiltonian that you ignore. There can be many directions in which your Hamiltonian is less symmetric than you think. There's an obvious thing, things that you don't know is the pulse distortion. So when you send the pulse down your lines, it will be distorted. And this is something that you don't know a priori. But the reinforcement learning algorithm can learn all this imperfection and optimize your pulse train so that you will get the best result. And this is what we call model-free reinforcement learning. We don't start from an Hamiltonian that we know. We start with an approximate guess, but the system will actually reconstruct the Hamiltonian of the system. It is allowed to so it is not simply adjusting the parameters of your supposed Hamiltonian. It is able to create more terms, if you want, in the description of the system. So that's very useful if you cannot calibrate all the skewness in the system, all the effects that you don't know about, the spurious effect that you don't know about. I would say that this improve the calibration roughly by a factor of 2. So in this experiment, there were two essential components: a better transmon, a state-of-the-art transmon, and this reinforcement learning calibration.
Okay. Are there any other questions? Okay, Michel, I have a couple of questions. One very quick thing about from your last answer, you said the transmon's high coherence, of course, played a role here. If the transmon was 2 or 4 times better in coherence, is there a simple scaling of what factor of improvement you would have obtained in your experiments?
Yes. So a detail I have to say. So yeah. So very important. I didn't want to flood the talk by too many details, even though some are very interesting. So here in this picture, I have represented errors by the simple model you have in mind, which is that the cavity can gain photons or can destroy photons. This is the mechanism you want to correct. Actually, because you're using a fairly imperfect ancilla, there are many more errors that creep in, which are due to the ancilla errors themselves. To give you to answer your question, Vijay, you have to realize the following. So in a cycle, 10% of the time we find an error when we apply the correction. That's good. That means that we run the cycle time is faster than the error rate. That's a good regime to be in. You don't want to correct. If you would correct an error every time you would run an error correction cycle, that wouldn't be so good. So this 10% is okay. But now we can analyze what error has happened during this 10% of the time that the system found an error. And 9 times out of 10, actually the error that is created is an error that comes from the transmon itself. So this whole error correction scheme basically corrects the errors in the error correction scheme, because how do you correct errors? You use this ancilla transmon, and apparently most of the time the errors come from the ancilla transmon. So indeed, if we could have a transmon which would be twice better, that would translate in an even almost a factor of 2 in the improvement of the experiment. So yes, you want basically, you would want to be in a situation where your hardware would be better. So one way to describe what I am saying here is that what we're correcting is actually the Hilbert space composed of the ancilla transmon and the cavity. And so we can really see that the experiment is a cooperation between 2 degrees of freedom, which by themselves are imperfect, but when we combine them, we can get a better qubit.
Okay, got it. So one maybe last question is, when one first learns about quantum error correction, from the Shor's 3-bit code, and you had mentioned that this is probably Shor's bigger achievement. There is a role of quantum entanglement there. And in fact, one often says that it's the entanglement and the fact that, we say environment can only do local operations. That sort of lies behind the principle of error correction. Is there something similar here to think about like entanglement? Because this is the same system. These are not separated systems where, the idea of entanglement and non-local and local operations can be brought in. So I was curious how to think about this here.
Yes. Okay, this is an excellent question. Well, entanglement is a little bit in the eye of the beholder. You see, entanglement means that you have 2 local systems, and they become they develop these correlations, even though they are separated. But separated can be taken in various can be understood in various ways. There's a geographical separation. So, for instance, in Alain Aspec's experiment, we said that the entangled photons are separated by some distance that is actually a space-like. But this is what I would call geographical separation. In an harmonic oscillator, if you look at the vacuum state, it involves a certain area in phase space, but there are other states that would involve different areas. So, for instance, when you make a cat state, you're using states which are far apart in phase space, and the cat state is an entangled state, can be viewed as an entangled state, even though geographically it lies in one cavity. But the cavity is itself an object that is not point-like. There are electromagnetic field at different places in the cavity. Okay, it's not very big. It's only a centimeter in size, but there is even there some geographical delocalization. So the modern point of view is that there is some distance in phase space, and a cat state, when the two blobs are very well separated, is actually should be considered as an entangled state. And in the same vein, the GKP state is a very profoundly entangled state of the information in the oscillator, in this sense, in the sense of mixing different local operators. Of course, if you the catch is that if you want to improve the fidelity, not of memory, but the fidelity of operations, then you need both this entanglement in phase space, this delocalization of information in phase space and in geographical space. So entanglement is the, if you want, is the phenomenon in which your information is delocalized, but this delocalization can be inside the phase space of 1 degree of freedom, or it can be spread among various degrees of freedom. But in quantum mechanics, you don't put on different footing the states that come from climbing the ladder of states in 1 degree of freedom and going to another degree of freedom. All the degrees of freedom are united in sort of bigger Hilbert space.
Okay, great. Thanks for giving a very clear answer to that question. Okay, so I think we can close the question answer session now. Let me thank Michel again and for this wonderful talk and these really exciting results. And I will hand it over back to Professor Deshmukh for any final remarks.
Okay.
Well, thank you very much, Professor Devoret, and thank you, Vijay, also for conducting the session. It really was amazing talk, and for me, it was particularly interesting how geometrical phase plays such a big role in stabilizing these things. So, Vinay, would you like to add a few comments here?
Yeah, no, yeah. So thank you very much, Professor Michel. On behalf of all the CAMOST organizers, IIT Tirupati and ISO Tirupati, it was really an enlightening talk describing this GKP coding, its experimental realization, and the error correction protocol. I think all of us have really benefited listening to this talk. Thank you very much.
Okay.
And thank you also to Professor Vijay for joining this session.
My pleasure. Thank you for your invitation. Bye-bye.
Well, Professor Devoret, the only thing I would like to add is it was nice to have you at this virtual meeting, but we will also look forward to an opportunity to have you here in India and visit Tirupati sometime. So,
believe me, I will take all opportunities. I have to visit India.
yes, and when you visit India,
I am always thrilled to
yes,
go to India,
and you must certainly come to Tirupati at that time. So, thank you very much, and I guess we can close the session. Vijay?
Okay.
Yes. Thanks, everyone. Bye.
Thank you. Goodbye, everybody. Thank you.
Bye.
Goodbye.